You squeeze me.
Okay. Hello, guys. How's it going? Any questions from the previous lectures?
Vita has 3 questions.
Okay.
Jeff, can you maximize the window, please?
What?
The window. Can you maximize it? The camera window.
Oh, I'm sorry.
Thank you.
Okay. Yes, I saw something is something is different. Okay. So what questions?
What are the limits of quantum computing?
Limits of quantum computing? Nobody knows. It's just it just started. It's just the way ahead is so huge. For now, it looks like there are no limits at all. There are calculations. Okay.
Following Penrose's theory, will quantum computers be able to overthrow humans?
Whose theory?
Penrose theory and his quantum mind.
Oh, and his quantum mind. Did you read Quantum Mind, Antosha?
Nope.
No.
Yes, I did. I wrote it.
Okay, guys, it depends upon us. If we're really weak, humanity, I mean, if we're weak, so they will take over. That's all.
Well, no, the question
If we remain strong, probably not. Okay.
But well, the question is this: according to Penrose, regular computers, the ones that are based on transistors, cannot become smarter than humans in principle, because they're too simple. But quantum computers, they kind of overcome that obstacle, right? By using quantums.
Exactly. Standard classical computers, they are algorithmical, right? Algorithms. We talked about this. We talked about this. And the neural networks and quantum computers, they work on different principles. They don't have these barriers at all. They don't. So even if you think about, the kids, if you think about this paradox that like finite and infinite, right? Finite and infinite. Are they really different, and are they the same? There are paradoxes. There are lots of paradoxes everywhere, but one of them, infinite and finite things, are actually very close. They may be transformed to each other. Like in mathematics, there are certain transformations that make like infinite finite and back. So you can work with infinites. Also, differential calculus differential. How does this say this term? Analysis. It's all about infinite things, integrals, differentials, and everything. So
all about infinitely small things.
And infinitely big too. They're the same. You can work with infinitely big things too, with the differentials. But anyway, it's not the thing we were talking about. But the point is that the whole idea that something can be only finite, it is wrong. It's fundamentally wrong. And Hilbert is very wrong in this. He was a great mathematician, but looks like they say he's a genius. He's not a genius. He could not look too far. And it started from him, from these finite things, finite algorithms, and all these ideas of finite things. So when you think only finitely, okay, you cannot talk about infinite. But all mathematics is about infinite. That's very very interesting stuff. And mathematics reached a lot with the concept of infinite things. So quantum computers, yeah, they don't have restrictions with this. Looks like that human mind doesn't have that restriction too, but in a certain way it's finite in its volume, right? Like we can make quantum computer with the size of the moon, like for example.
The Death Star.
Yeah, but another thing which Penrose is actually thinking, if you look deeper into his book, he has some hopes that human mind is actually connected to the quantum world. So we can access these quantum processes everywhere in the whole universe. In this way, our mind is infinite as the universe, right? But unfortunately, he didn't find this gateway to heaven or whatever. He didn't. So he had some ideas, but he didn't. That's another story. So, but anyway, quantum computing, they don't have restrictions. Okay. Other question, or these are all three?
Third question.
Okay.
According to Moore's law, in 100 years, how many computations would a quantum computer foretake?
How can what? I didn't get what. Moore's law, okay. Doubling right now for quantum computers, it's doubling processing time and power, doubling each year. So each year it's doubled. So what was the question further? I didn't get.
In 100 years.
In 100 years.
In 100 years, how many computations would a quantum computer foretake?
Oh, there's a formula, geometrical progression, 2 to the power of n, where n is the number of years. So doubling 2 to the power, and you can take your calculator and calculate. It's 2 to the power of 100. It's about 10 with the 30, 33, something like this, 33 zeros. Years. Oh, not years, calculations per second, right?
Ooh.
Something like this. And you should multiply it by the amount that you have now. We right now, what's the speed of it? I forgot already. So you can take power. You take the how they say this? Speed, not speed, rate, right? Processing rate. How many flops you have, and multiply by this 2 to the power of 100, and then you'll get how it will be in 100 years. That's a lot. It will be like a huge amount. But the interesting thing is about mathematics that whatever big amount is, whatever big value is, right, there is a transformation which can transform this infinite or very, very huge thing, even infinite number, into finite number. So, and that's interesting point. So probably we can still work with it somehow. We don't know how yet. Okay. Okay. That's all for now. Questions? No.
No.
Okay, guys. Huh?
I was trying to read about it, but I understood nothing.
Sorry.
I was trying to read about quantum computing, but I understood nothing. I understood a bit.
Okay, I can add for quantum computing. I can add maybe a little. Maybe just do not. I just don't want to overcomplicate things. But in a certain way, quantum computer is a quantum neural network. Actually, it is not used like this right now for certain reasons. Many reasons. One of the reasons is that people like to think in the old way, not the new ways. But it works like neural network with the unlimited amount of connections. And this is a very powerful thing, actually. And neurons in our brain, they works basically the same way. That's the whole idea.
Well, that was what what's his name? Hilbert. No, you know the guy with the D, the one that with the theory that you did the question with for data. What?
Penrose.
Penrose, yeah. It's like Penrose's theory.
I don't think so. No, he was thinking about something else. No, he was looking for some special features of neurons in the brains and the human brains, and he was thinking that somehow these small elements, they can be connected to the to the quanta in our body, but I don't think the ideas were really good. He's mostly a mathematician. He's a physicist too, but the ideas, they're not that deep concerning physics with Penrose. But anyway, he's a good guy. He's a very interesting guy. Yeah, but this idea fails actually. Okay, so let's do this, right? Okay, there's a numbers and names number 20, and this And this lecture will be the last for this summer. Then we'll continue in autumn, right? So that's I want just to tell something that I promised you to tell. Some months ago or a year ago, something like this, I promised you to tell some story about moving in space and time. Remember? We spoke a little about this.
Yeah, I remember.
You remember? Okay, so just I have to talk. I want to talk about this a little because mathematics is closely connected with all these ideas. You may think about them. We may talk on them later. So, and maybe it will produce more questions on your side, and your brain starts working. At least we have to overcome these quantum computers, right? Okay. So the SpaceTime machines. It happens the way that traveling in time and traveling in space are very closely connected. And the idea why it's connected is because all that we see around us, like we are, right? And we see like for example our sun.
Where is my son?
It looks like this, by the way, from space.
Really?
Something like this.
That's like a ball.
Yeah, there's solar flares, protuberances. There's okay, so something like this. Okay, so when we see the sun, actually we see not the sun right now, but we see the sun, which was 8.5 minutes ago. So sun is about 8 light minutes, right? Light minutes from the Earth,
Oh, no.
right? The closest star, it's Proxima
Centaurus?
Yes. It's about 4.5 or something like this.
Million.
Light years, right?
Oh.
So
I thought it was 1 light year.
no. 4.5 or 4.3. I forgot exactly.
Wait, that's a galaxy.
No, galaxy is okay. We'll maybe talk about galaxy. So it takes 4.5 years for light to travel from the closest star to us, right, to the Earth, right? The closest galaxy, right? Andromeda. It's about 1.5 million light years.
Oh, man. So we see it 4 million years ago. 1 million. 1.5 million.
Now the Big Bang, when the whole universe started, right? It has distance too from us.
What?
Yes. And the distance is about 13.5 billion.
Oh.
Billion light years.
So
Which is often said that this is the size of our universe, right? So the light from the Big Bang, traveled to our Earth 13.5 billion years, and we can see it actually. I saw it. I saw it myself. Many people of my age saw it because the TVs that we had those days, they were not cable TVs. Right now TV is cable, right? Through the cable, give signal by the cable mostly. By the old TV, they have these antennas like this TV, the screen, right? And there was like antennas.
Oh.
Which took signals from some station far away. But in addition to the station, or when the station is down, right, for some reasons, right, it was getting cosmic radiation, cosmic radio waves, which comes from space, and you could see them on the screen.
Oh wow. It's cool.
Not the whole image was. It's about like 10% of the image was this these waves that actually is the light from the Big Bang.
Woo.
But while traveling, it become not the light, it become radio wave. Because there's a so-called red shift that the
I have a question. Did it happen by accident?
No, it's just like the noise. These antennas of the TV, right? And they happen to be in the same getting the same frequency that actually are traveling from the Big Bang. That's all. Just it's not an accident. It just happened this way. So it was called some kind of background radiation or whatever, different ways for this light from the Big Bang. But right now it's not light, because while traveling these billion years, what happens with the light? Actually, at the first it was high frequency, and then it become lower and lower, like this. So here it is light. It's all one wave, right? Here is light, but while traveling it become radio wave. Because
still see his light.
Huh?
No.
Well, you can still see his light?
No, we cannot, but we can see it on TV, because TV transforms radio waves into the light, right?
Oh, okay.
So that sort of interface, sort of visualization device, TV was like this. Okay, so what I want to say, that everything that we see around us, including like for example, our hands or our legs, right? They are too from our eyes. They have some distance, right?
Yeah.
So it takes some time for light. So probably some so-called picoseconds or something. Pico at like 10 minus 12 or something second. Some picoseconds to travel from your hand to your eyes. So even if you even if you look at yourself, you see not yourself. You see yourself in the past.
In the mirror? In the past.
In the mirror, or just when you're looking like this at your hand. You look at your hand, right? The light goes from your hand to your eye, certain time.
And then through your
So your hand is in the past, in relation to your eye. So everything that you see around is in the past. So all this around is past.
But I have a question. So if I saw something that happened to my hand, it happened like a few something seconds ago. Picoseconds ago. But you didn't feel it.
You can calculate how you have the speed of light. By the way, you can calculate. You know the speed of light, right? It's 300,000 kilometers per second, right?
Yeah.
It's 310 by 10 to the power of 5 kilometers per second, or 3 to the 10 kilometers. How many meters there? In kilometer. In kilometer, 1,000, right? So you should add 3 here, so it will be 8 meters per second, right? So you can calculate from this, if you know this number, how much time will take for the light to travel from your hand to your eye, and you see how far in the past your hand is to relation to your eye. Just calculate it as an exercise, okay? So everything is in the past. This is first point. Around us. The second point is, I mentioned it some time ago, it's very interesting and paradoxical, that actually for the light itself, when it travels, it doesn't take time at all. There's a what's the name? Pythagorean? Pythagorean, what's his name? What's pronunciation?
Pythagoras.
Huh?
Pythagoras.
Pythagoras, right? So, okay, well, let me X for example. So this is the Pythagorean theorem, right? In space-time, for space-time. This is the distance in space-time between 2 points, like A and B. And D means that it's small thing. Small amount. You may write like this too, without D.
Wait, D is slow?
D means that it's small value of tau or t. This is called proper time. So proper time is the time actually which feels the particle itself, which is moving. Like for example, photon, the particle of light, right? Photon, it's his time. Tau is his time. So interesting enough, when traveling from point A, like over Big Bang, for example, right? Point A to us, which is point B, right? Here we are. And here's Big Bang. For us, it is traveling 3.5 billion years, right? For the photon is 0. Proper time for photon will be 0. Tau will be 0. So it doesn't take any time to travel for photon from point A to point B. This is the paradox of theory of relativity, and it's experimentally tested thousands of times. That's true. So A and B looks like they are very different to us, but to photon it's actually they coincide. It's 1 point. A and B comes to 1 point. A
I have a question.
or B. Yep. Okay. For photon.
If quantum can be anywhere at any moment, like from Earth to the edge of the universe, then would you say that it's faster than the speed of light then?
No, it's not faster. Actually, the same guy Penrose, maybe I told you already this, he actually proved mathematically, that for any particle, it actually travels with the speed of light only. So like photon, any particle.
It gets into the universe faster.
And so when you travel, okay, just example, when you travel, okay, you understand for photon it's 0 time, right? I wrote it just, I need some room for this, right? Okay, if you have photon or any other particle, right? And this is universe, right? All this is universe, right? And it travels like this, for example. And it goes and touch each and every point in the universe with this path, right? Long path. The path is very long, right? But however long it is finite, because there is a finite amount of particles in the universe. Remember, like 10 about 80, something like this.
But
yeah, wait. So the length is finite, and even if it's infinite, but anyway, it's finite. So but the photon, it is still the tau still be 0. So for 0 time, he touched each and every point in our universe. So it is everywhere. For himself, it's everywhere. At the same, all these points for photon or electron or whatever, all these points coincide. It's all 1 point. It's always point A, B, whatever, and 10 to the power of 80, right? Points, right? They're all 1 point. Just point A. It's here somewhere, Big Bang. And that means that it's everywhere at the same time for himself. And when we look at it, it looks like that they are in some other place. Here, this place, or that place, or that place. But actually, they're everywhere. This is a paradox again. But this is how it's in quantum mechanics. Exactly like paradox. It's formulated like paradox. So what's the question again?
Never mind.
Okay, but you got the idea, right? So it is very closely connected. This thing and quantum mechanics, they're very closely connected things. So, but it's just answering this small question. Now what I want to talk, and yes, and again to mention that according to Penrose, even electrons or protons or whatever, neutrons, the main particles of our matter, of our universe, right? They all travel with the speed of light. Just it looks like for us that they have some certain speed, but they have speed only c, so speed of light. So the same thing for each quanta, each electron, each proton, each neutron, whatever quanta is, their own time, their proper time to reach any point in the universe, it's still zero. So for any of these particles, their time for reaching any point of the universe is zero, exactly. Yep. But it looks like it's relativity, right? The relativity is that from his point of view, from this quantum point of view, yes, it's zero. From our point of view, it may be billions of years. That's interesting paradox that we're talking about. But we start from this, and what we see right now, just take a look. Okay, let's look at the photon, right, which started at Big Bang, started here, right? And it travels to us. We're here, right? To the Earth, right? And then it travels somewhere further. Like here it is, for example, 3 billion, right? Light years ago, right? So it is past. And let it travel there, 3.5 billion years ahead. So this is future, right? So the photon in how 13 plus 13, how much it will be together?
Okay, I have a question.
Just wait, before, just how much should be this and this together? 27 billion, right? 27 billion years, right? So this thing is 27 billion years in the future from the Big Bang, or 13.5 from us. Okay, what's the question?
I have a question.
Sure.
Can anything only be qualified as living if it can die?
That's a little off the topic, right?
Yeah. I'll just ask it at the end.
Ask it at the end, yes.
So
what was it? Yes. What? Sorry, I had to take a phone call.
You take, okay, whatever.
Okay.
So Vitya, let's talk about later, okay? It's not about, okay, just write it somewhere, okay? We'll talk. This is not about this, right? Something else. So just look at this picture, right? This photon is traveling, it reached us, and then it goes further to the future, right? But for the photon itself, all these points on this line, they're just one point. It's just zero, right? For photon tau is zero, so it's just 1 point there. And not many points, just one. All these points coincide. A, whatever this point, B, point to the future C, any other points on this way, are still the same. So what it means, actually, this is distance, it's actual distance. Distance is measured in time. In space-time, distance is measured in time. Light years, it's actually time. It's years, right? So it's all measured in time. Space and time measured still in the time units. So it's still time. And the time is zero for it. So it's in 1 point. So what it means, actually? It means that actually, if this photon is changed, right, somehow, it is changed everywhere because it's just 1 point. Here, just one. All these points are connected to each other, just 1 point. If you change point here, you change it everywhere. If you change point here, you change it everywhere also. You cannot, if you have only 1 point, right, you cannot change it without changing other. All these points are in one. It's a paradox again, but just think about it. It's a little interesting thing. It means that all these points are connected.
Sorry, never mind.
So you changed something here. Photon passing you changed it somehow, right? So in the future it will go changed, right? Everywhere. It's already changed here, so to the future will go changed. But because this point is the same as this, actually it will be changed not only there, but here too. Whatever you do with photon in one point, it will be changed in all points on his path. It means that our past, our present, our future are closely connected.
That's interesting how that...
And how, just think about it, and how it will go, I'll tell just in a couple of minutes, okay? Do you know how your projector, you use your projector, right, to watch movies, right? In your basement, right? Do you know how it works?
I have a book about it, but I lost it.
Okay. Anyway, so the idea of it, it's about lenses and mirrors, spherical mirrors. There's a formula of lens. Lenses usually they mark it like this. You know, this is the line. It's called optical axis. Optical.
It's kind of like eyes.
Optical. Right? Yes, eyes are lenses. Yeah. Optical axis.
It's based on eyes, right?
Well, no, the eyes are. Well, yeah.
I know it's more complicated, but it's kind of based on it.
Yeah.
So each lens or spherical mirror or parabolical sometimes, they have the certain point which is called focus. And it's usually, for the lens, there are two places for this focus. They are the same, distance is the same. F here and F here, right? So what happens actually, there's an easy way, if you lost, maybe you remember this, there's an easy way to create a picture which is simple, of course, simplified picture what lens make with your image, right? For example, you have some object that high, like for example a person, right? Here. What lens do? Actually, when you have some parallel light going like this, parallel to the optical axis, parallel, right? Lens turns it to the focus.
Using a mirror?
No, your mirror do the same, just a little, just because mirror reflects it, right? So it's to the same direction. If you put mirror here, right, so it will go like this. Okay? Pam, spherical mirror will go to the focus. And the same thing if you go like this way, right? So what we do, and there's one rule is that if you put light, the way of the light, through the optical center, it's called optical center, the center of the lens, right? It goes like this, through the optical axis, just that. So for example, if you put it like this, light goes here. And to create image, which will be created here, you do the same thing. You put parallel, like for example, photon going parallel to the optical axis here. And it will go to the focus, right?
Yeah.
So if you go to the focus, just do it here, and here they intersect. So this will be the image of you here. Just head down. That's how you create pictures. From this image to this image.
These pictures are upside down.
You may do also like this. Go through the focus here.
See, you flip it.
And it goes like this, parallel to the axis back. So there are few lines how you do it.
Is it upside down? The other one flips it back up.
Papa will explain it further for you. And also nice to know, maybe there's a good, it's called formal lens. This is like this. A and B are these differences, these distances, A and B. And F is this, right? Focus length. So this is the lens formula. So that's how you create it. But the main thing what we want to show, to look here, that actually lens or mirrors or whatever, they can create your image somewhere else. You are here, but your image is here. And interesting enough that this image is actually material. It's not like some imagination. The image that you see on your screen, right, actually it is real light. This real light goes from certain image here, right, so certain photons. Photons are actually, remember, E equals mc squared, right? So if photon have energy, and each photon have energy, it has a mass, so it's a matter. It's a real matter, material thing. So these photons go from here, and then they come here and they create material image here. You have material image here, you have material image here. But for the photons, there are only photons here. So this is photonic, you can say photonic object.
That's what it's called. Because it's photonic.
So it consists only of photons. This thing. This is a quantum object, right? That's less for quantum object. It consists of different quantums, different matter, different types of matter, right? But this image consists only of photons, so it's photonic object. Not all the particles really place here. Not all the particles, just photons, right? And there are two main things here. One thing is that photons takes some time for photons, from our point of view, to travel, right? So this image and this image are actually different in time. From this point of view, this image is in the past. And from your point of view, this image will be in the future. Because it takes some time to go there.
But if it took some time to go there, wouldn't it be then how did you control it if you're in the past?
You're not controlling, you're just sending your image like through the system, right? And it will appear there in the future at this point. You don't see it right away, but you'll see it later, right? So it will come there. It's for you, but the photons, it's just the same. It's right here and there at the same time. For photons, they are here at the same time. So it means what? That if you change your photonic image here, you will immediately change your photonic image here. And backwards too. If you change it here, this will be changed too, because they are the same from the photon point of view. And actually, it's paradoxical enough, but in quantum mechanics, these things are experimentally proven. So there are experiments, lots of them, which actually prove that. The most paradoxical experiments in quantum mechanics are connected exactly with these things. That when you change thing in the, like for example, in the future or in the current time, in present time, it is somehow changed in the past. And there are lots of attempts to find out how to deal with it, right? Because it's paradoxical, but the solution was not found actually. So this is just a reality that we have to deal with. So with this simple picture, you see that changing here will change it here. So changing in the past changes the future. That's actually a pretty simple thing. When we change something here, right, the future will be different. That's, we know, everybody knows that, right? We broke like a building, right? The building will be broken in the future. So we change the future by doing something in the present time, right? But interesting enough, that with quantum mechanics, if we deal with quantum mechanics really, it happens backward too. If you change your present time, you change actually your past too. And this is proven, but not that easy. So that's you may talk, there's lots of talks maybe done on this, but just for now, just a little think about it, okay? So their future, present, and past are closely connected. And quantum mechanics, it is the experimental proof for this. This is theory which proves this connection. And the formula of this connection is still that relativity formula. It's this one. So which means that for photon or for electron, for proton, for whatever, it doesn't have time to reach any point of in the universe. It's zero time. Now the only thing that's now just think about this projection, right? So if you create projection like you have in your room, right? Something like this, some parabolic mirror, and you put yourself here, right? And this can project you somewhere in the future. And you will travel with the speed of light. If you are photonic, so consist only of photons, but you consist of other particles. So you have to find certain way to send you with the speed of light to the future.
Wow.
And there is a way. There is a way. Because
and then that would be a time machine.
It will be a time machine to the future, right? And also the space machine, because you will travel with the speed of light with a certain time of, like if you travel for a year, right? You will pass exactly one light year, right? You will get 1 light year somewhere ahead. So if you go to the Proxima Centaurus, right, 4.5 years, right, you will reach Proxima Centaurus for 0 your own time, for 0 proper time for you. But if you look at it, you will still be traveling for 4.5 years to this Proxima, right? So you will travel and travel and travel and traveling and then reach it. So it's a space and time in the future. So this is for projection, right? Now, if you just look in the telescope, there is a certain image of a certain, like you in the past, right? Somewhere in the past. Somewhere on another planet. And you watching it with a telescope. Telescope is exactly a projector, just inversed. It does not send your image to the future. It takes some images from the past and creates some image here from this past. So this is present and this is past. But these images are connected the same way like they were connected in this picture with the lens that I told you. So if you change it here, it is changed here. It means that if you have here the picture of the planet, right? Some surface of the planet here. And if the surface is photonic, if you go into the surface, you are here at the same time.
Oh.
And this means, again, you passed this space, but back in time. Back in time. So you are here. So if you are made of photons only, not other particles, right? You can easily go into the image from your normal telescope. Go inside it. And you will find yourself exactly on this planet. Right away, at the same moment. And this will be back in time too. Because the planet that you see, it's back in time. It's in the past. So telescopes and projectors, right, are actual time machines, but only for photons. So for photonic matter. So one special type of matter, which is still matter, is material, but so you can right now It's not these things that exist right now, right? So it's not about talking something in the future. They exist now. So for now, for photonic matter, telescope is the time machine, and projector is a future machine to the future, or starship, because you travel somewhere into the future, and you pass. Of course you get some space when traveling, right? So this is photonic matter. So the only question, how to create the real time machine and real space, like spaceships or whatever, right, with the same idea, is how to create these telescopes and projectors, not only for photons, but for other particles of matter.
Yeah, for us.
So we consist of electrons, protons, and neutrons, and photons actually too, So if we take all these particles and we create these telescopes and projectors for these particles, we can travel in space and time. As easy as now photonic images are traveling back and forth with the telescope and projectors.
Wow.
And interesting enough, it can be done. Not today, but in some future. It can be done, but the idea is just because quantum mechanics says that all these particles, actually, they are not only particles, but they are waves. They're particles and waves. Quanta. Each quantum is particle and wave at the same time. And if you is a wave, you can create telescopes and projectors for the waves. They're a little different. Like for electrons, we already have telescopes and projectors. We don't use telescopes, but projectors we used. It is called electron microscope. You probably heard of it. Heard of it?
No.
No?
Yeah.
No? Yes?
I have it.
Electron microscope, it's more powerful than the regular optical microscope because it is using electrons instead of photons.
They're smaller.
Also, there are proton microscopes too. So we are going this way. And what I'm saying that we are already doing these things. We really created like microscopes. Microscopes is how it is built. It's very close to the telescopes and projectors. The same optical scheme, just we use not glass lens but something else, magnetic lenses, called magnetic lens so magnets like circular magnets. They create lens for electrons and protons, charged particles. Also, there are optics for neutrons too. They're not that developed, but they exist. But they exist now. So we are moving this way, and going this way, we can actually really create the real time machines and spaceship, and travel to any point of space time for zero time. So to reach any point in the universe, in the future or in the past, with zero proper time. So it will take 0 seconds for us to reach any point of the universe, whenever it is, in the future or in the past. Maybe just for you to add and to finish this thing, how it can be done in the future. The easiest way, how it looks like from now, it is to create so-called neutronium matter. Neutronium matter is a type of matter which actually neutron stars consist of, and neutron stars, we know that they are in the universe, so it's a very existing thing. Then our atom nuclear, they consist of mostly neutronium matter, but in addition, so protonic matter and something else. So it is something that we know it exists. We just cannot do it right now in the lab.
And we have it in us?
Pardon me?
We have it in us?
Yes, we have it in us. Yes, actually, our weight is mostly, believe it or not, is neutronium matter. There's interesting phenomenon which is called modulation. Modulation is used in our radio wave systems. You know how we see images in the on TV or maybe in radio, right? We send radio waves, right? Radio wave is a electromagnetic wave of very high frequency. It goes like this, like oscillations, you know, like this. Electromagnetic field goes like this, up and down, up and down, up and down, right? And very fast, like millions oscillations per second. But usually we want to send something lower frequency, not like this, not millions, right? Like, so for example, we want to send sound, right? Sound, and sound is about 100, like for example, 100 or 1,000 per second. So it's much lower frequency, like 1,000 times lower frequency. So how it is done actually? It is done with modulation. And modulation means like this. So instead of sending this wave, electromagnetic wave, right? We send wave like this. So this is high frequency, but this is low frequency. This is actually wave with the same frequency as sound. And this process is called modulation. And this is what about most of the radio systems is about. They are doing these tricks with modulation, right? But the same modulation can be done with the regular quanta too. If you send like a wave with very high frequency of neutrons are waves, so you have very high frequency wave, right? And we modulate with regular matter. You will see the same picture like this. And this wave, it is the regular matter wave.
And what is the carrying frequency?
Pardon me?
What is the carrying frequency?
This is carrier, yeah, that's the term, yes. This is called carrier frequency. This is neutronium.
What is it?
Neutronium, neutron wave.
Okay.
This is neutron wave, which is modulated by the other particles like as waves too. The frequencies of actually the structure of our body, right, is actually much lower than the frequency of neutronium wave, whatever you take it. It's much lower because there's other main formula which you see too, which you saw. It is the main formula of quantum mechanics. That's the energy. Is that how connected with the frequency? And H is so-called Planck constant. The structure of our body, everything that's our body, including our thoughts and everything, right? This structure is connected with certain frequencies, and these frequencies are much lower than the frequencies of the neutronium. So by modulation, we can do the same trick that we do in radio wave propagation, TV, and whatever, and send us to any point of space-time. Okay, guys. Questions?
No.
Did you say this was the last lecture?
For this, yes.
Huh?
Yes, for this summer, right? So we'll continue in autumn time.
In September?
Yeah, September, October, I'm not sure. Probably October, close October, not September.
So there's going to be nothing next week and the week after until October?
Yeah.
Mm-hmm. What about next year?
What about next year?
Will there be more lessons next year?
October, this is not next year. October is this year.
No, but this
Oh.
Will we have it next year? Will we have it next year?
What?
5 months. But will we have it next year? Papa.
Will
we have lessons next year.
We're talking about this October, so is it next year or this year?
Next.
If you start this October, you will go to the next year too, I guess, right? Or
no. No, I just mean next year. Are we doing it?
Yes, we are.
You have, yeah, everybody should have vacation, right? This is a summer vacation. So we have summer vacation, then we start continuing, right?
We don't need a summer vacation.
Yeah, right, okay. So I need then, okay, guys?
Okay, well,
but anyway, I am open to all questions. We can talk, right? With no lectures, but we can talk on Skype or whenever you want to.
That doesn't work, you know that.
Okay, but yeah, but if you're really, eager to find something, you can ask me, no problem. Okay. You can call and talk, right? And we can speak on Skype too, if you want me on Skype.
Are you going to put the videos on the internet?
Yeah, going to, yes. I should find time for that. Yeah. Mm-hmm.
Okay. Okay, well, that was really good.
Okay, guys.
Well, can we talk to Bob now?
Sure. Just a moment. Yeah. And, yeah. Okay. By the way, did I mention or not that this thing actually was reported in 1990? The main idea of this. The main idea of such travel was in 1990 in Kaluga. Kaluga, Soviet Union.
Oh,
really? Really, yes.
Oh, wow.
By me. Okay. I am calling Babu. Okay, see you soon, guys.
Yeah.